And welcome all of you to Members EduI. So following the previous speaker, I will also introduce a cluster of 3 topics instead of focusing on a single problem. So my work, as I mentioned, is mainly about secure and trustworthy AI. And in this presentation, I'll be mainly talking about some of our work in improving the robustness, privacy, and fairness of collaborative learning. Okay, as you all know, collaborative learning, where multiple entities collaborate with each other in order to achieve a more accurate or more useful model. And the key premise is that they don't share the raw data, right? So that is the core premise of collaborative learning or federated learning. And one of the common assumptions is all the clients are honest but curious. So basically, they want to find out the data about other participants. It could be the clients or the server. They want to find the data about the other participants, but at the same time, they want to reveal as less information as possible, but they honestly follow the protocol. And as Mike introduced in the morning, there's a federated setting where you have a central orchestration, or you can also have a completely decentralized collaborative learning framework where there is no central orchestration. It's just all the clients directly talk to each other in a peer-to-peer fashion. Right, so my work is motivated from concepts in biology, right? So basically, if you look at nature, right, when people or organisms or species collaborate or live together, there are various possible types of collaboration, right? So one is, the most common one is mutualism or symbiosis, which many of you might have heard about. So this sea anemone and jellyfish, where both the organisms kind of benefit from each other by living together. But that is not the only prevailing principle in nature, right? So there is other things like commensalism, where one organism benefits, the others don't get any benefit, or at the very least, they are not harmed, right? And then there is parasitic behavior, where basically there are some species which try to live by essentially harming others, right? And finally, you have a competition kind of scenario where different organisms are competing with each other for the same resources. So basically, my goal is to develop collaborative learning algorithms for this non-mutualistic scenario. So when there is communalism, parasitism, or competition. So how do you handle these kind of scenarios? So basically, it boils down to 3 main problems. So one is, instead of just focusing on accuracy and efficiency, we also need to look at things like Byzantine robustness, which Samuel introduced in the morning, right? So you have algorithms which should be resilient against selfish behavior by malicious participants. The next thing is what happens if the privacy is compromised. So most of the federated learning algorithms, they just focus on data confidentiality. The raw data is not shared, but some updates are shared, and that might leak sufficient information about the raw data. So how do you prevent this leakage? And finally, the issue of collaborative fairness comes in, which again Mike alluded to in the morning, right? So you need to have proper incentives for collaboration, and these incentives have to be fair across different participants. So how do you ensure these 3 properties will be the focus of my work? So the first problem I'm going to address is about Byzantine robustness, where you have clients, malicious clients, which are trying to subvert the learning process by introducing poisoning updates, right? So how do you handle this kind of scenario? So one of the works that we propose is, okay, so you have updates, you have a server which is trying to aggregate updates from different clients, but then the server can compute either directly from the updates, they can do some kind of clustering, which is the main focus of the previous work, and they can try to find out what are the outliers in those updates, right? So that is one possible approach. But in this work, what we do is finding these outliers is very difficult directly in the model space or the update space. So what we try to do is try to compute distances or similarities between these updates, and then try to find the outliers in this distance space, which seems to work much more effectively than directly trying to find the outliers in the update space. So this is one example of our work. So where basically we show that, so in this case, the first one, there's no attacks, like all the clients are honest, right? So in this case, all the clients contribute to the learning process, and it works as well as federated averaging, which is the most common aggregation approach. But in cases where, let's say, some of the clients are malicious, right? So in the second example shown here, you have a 10% level flip, which means like one of the clients is malicious among the 10. So in this case, we are able to clearly identify the malicious participants even in the very early rounds of collaboration, and then kind of suppress their updates so that they don't affect the learning process. And we can do this across different types of noise and different number of malicious clients. It does not have to be one client, right? So you can have up to, let's say, close to 50% of the clients can be malicious, and we can still continue with the learning process without any problem, right? So as long as the majority are honest. Okay, so the next work I'm going to talk about tries to address the privacy issue. So as I mentioned, most of the federated learning algorithms involve sharing of some updates, typically gradients or model parameters. And the problem with that approach is, though it is not the raw data, if the server has sufficient resources, it can try to do different kinds of gradient leakage or reconstruction attacks. From basically using these updates, it can try to reconstruct the actual data which was used to generate these updates. Right? So then there are different methods to address this problem, such as differential privacy and so on. What we try to do is, okay, the main problem comes when you have a centralized server coordinating all these activities. So why not go for a completely decentralized approach? But in this case, how do you preserve the privacy? So that is where we use the concept of fully homomorphic encryption. Right? So what happens in this scenario is you have multiple participants. They are trying to collaborate. So it's a mutual knowledge distillation kind of scenario. So each of these participants is a teacher to the other participants. So now the problem becomes, how do you distill knowledge from one participant to the another, and without leaking your private data? So we use this concept of fully homomorphic encryption, or FHE. So you encrypt your data, and then you can actually publish your encrypted data. Since you are the one encrypting it and you are holding the key, nobody else knows anything about your data. What the other participants can do is simply get this encrypted data, use their own local models to make predictions in the encrypted domain. So they don't see what are the predictions, but they just do an encrypted inference. And the third thing that happens is you need to somehow distill the knowledge, right? So for that, you need to compute some distillation loss. So we also show that this distillation loss can be computed fully in the encrypted domain. So which means the participant, let's say you have participant 1, the participant 1 just publishes his encrypted data and also an encryption of its own predictions on this data. And the other participants can just make their own predictions and compute this distillation loss in the encrypted domain and return it back to the participant 1. So then the participant 1 can actually go back, decrypt the loss alone, right? So they don't get any other information. They just decrypt the loss and use it for the distillation process. So one of the key challenges here is, how do you compute the loss in the encrypted domain? So we, in this work, we use the KL divergence as the distillation loss. And if you can expand on the KL divergence, you can see that there are some quantities which can directly be computed in the encrypted domain. There is this log sum exponential term, which is very difficult to compute in the encrypted domain, because in FHE domain, you can only do linear operations, right? So you can do additions and multiplications, but it's very difficult to do nonlinear operations like exponential and log. So we show that some of these terms can actually be approximated. Actually, you can remove them completely, or you can approximate them. So that allows you to compute the loss in the encrypted domain without sharing any private data. So this work, we try to compare it with the standard federated averaging and the federated averaging with differential privacy. So the thing is, federated averaging usually gives you very good, the numbers reported here are collaboration gain, which means what is the gain achieved by a participant compared to just a standalone model, right? So in this case, we show that fed averaging gives you very good collaboration gain, but as I mentioned, it is vulnerable to these gradient leakage attacks. So our approach, which is known as CapRide, it achieves much less collaboration gain, but then it is much better than actually doing fed averaging plus differential privacy, right? Especially in cases where you have smaller number of clients, because there, in order to protect your privacy, you need to add a lot more differentially private noise compared to the case where you have many participants in the process. So this is more applicable for the cross-silo setting rather than the cross-device setting. So in cross-device, you have millions of clients, and then each client can add a little bit of noise and get away with without leaking any information about their data. But in the cross-silo case, if you really want to achieve good accuracy, you need to add you need to add less noise, which is reveals your private data. So this approach works better than Fed averaging plus differential privacy. So the last work which I want to introduce is about collaborative fairness, right? So morning's presentation Mike introduced, right? So you have multiple entities collaborating in a federated learning setting or in a decentralized learning setting. The key thing is how do we incentivize these participants? And in this work, we are mainly looking at delivering differentiated models. So the incentive is not financial incentives or economic incentives, it's more differentiated models where the clients which contribute more actually get more benefit in terms of more accurate or more better utility models. Right? So in this case, how do you quantify the collaboration and how do you quantify the fairness? Right? So again, we kind of go back to this decentralized learning approach. So what we found is that when you're learning this, doing this mutual distillation, you have a local cross-entropy loss and you have a distillation loss from the other participants. So by looking at the alignment between the two losses, right? So in this case, you can find the cosine similarity between the two gradients. You can actually see which clients are contributing more to the learning of your model and which clients are contributing less. And then we can come up with a different weighting mechanism. So you can compute a reputation score for each of those clients. And also we can come up with an adaptive sharing mechanism where you can say, okay, if client B is contributing more to my model, then I will share more with B compared to some other client which does not contribute to my model learning, so I will not share anything, any updates with that client. Right? So you can adaptively control the sharing, and that improves the collaborative fairness. So one main issue when you're talking about collaborative fairness is how do we measure the fairness in the first place? Right? The standard definition is, okay, the clients who are contributing more should get better or more accurate models. Right? And the standard metric used is correlation coefficient between the contribution and the rewards received. So usually the contribution is measured in terms of standalone accuracy, which means if your client already has a very high accurate model, then it's contributing more to the collaboration. And then the reward is measured in terms of accuracy after collaboration. So in this case, I'm showing a simple example where there are two clients. So you have client 1 and client 2. They have the standalone accuracy. And if you see the accuracy after collaboration, clearly the client 2, which has higher standalone accuracy, has higher accuracy after collaboration. So in the sense of this particular definition, this is a perfectly fair system. But the issue comes if you look at what is happening in terms of the individual participants. So the blue line in the middle is a zero collaboration gain, which means the accuracy before and after collaboration are the same, right? So that is a zero collaboration gain line. And if you see this client on the left gets high positive collaborative gain, which means it's gaining from the collaboration. Whereas the client on the right gets a negative collaboration gain, right? Maybe the worst case is like, okay, it can just discard the collaboratively learned model and then use its own local model. In that case, it gets zero collaborative gain. But then this goes against the notion of fairness, right? So the client on the right actually makes more contribution to the model learning, but only the client on the left benefits from that. Whereas the client on the right, which makes the higher contribution, is kind of punished. So we need to have get algorithms that ensure positive collaboration gain for all the participants. And at the same time, we want to minimize the collaboration gain spread, which means the variations in the collaboration gain among these different participants. Right? So that is the kind of thing that we try to achieve. So we using this previous approach, which I just mentioned, where you try to compute the reputation of all the participants and then adaptively share. So we were able to show that we can get better positive collaborative gain, at the same time minimize the collaboration gain spread by using our approach. So especially in the imbalance setting. So if you have IID data or even heterogeneous data to some level, you can still achieve good positive collaboration gain for all the participants. So the two figures on the left, right? So here the ones shown in red is the local accuracy or the standalone accuracy, and the blue is the outermost blue square, the blue pentagon is basically the Fed averaging accuracy. So clearly in these two cases, you can see that all the clients benefit from the collaboration. But if you go for a highly imbalanced setting where you have some clients which have large amount of data and which are contributing more, and you have other clients which are contributing very little. So you can see that the client with the highest contribution actually suffers in federated averaging. They have a negative collaboration gain. And our proposed approach addresses this issue. So to summarize, basically I'm more interested in designing collaborative learning algorithms for these non-mutualistic scenarios. And mainly there are three issues. One is how do you handle all these conflicting requirements? It's very easy to come up with a scheme that achieves fairness or that achieves that is more robust to heterogeneous data and so on. But there is very thin line between heterogeneity and malicious behavior by a client. So how do you differentiate these scenarios becomes a challenging problem. And then there are inherent contradictions between privacy and fairness, right? So if you want to achieve higher privacy, you need to reveal as little data as possible or as little information as possible. But then that is not always possible if that actually contradicts with your ability to design fair collaborative learning algorithms. Also, there's need for better contribution assessment and practical incentive mechanisms. Thank you.
Questions for Karthik? I'm curious, so you mentioned you built this reputation system. How is this reputation calculated? Is it based on these cosine similarities you mentioned? Or?
Yeah, based on the cosine similarities. So what we do is we take the cosine similarity between your local loss or gradient based on your local loss as well as the gradient based on your distillation losses. And if they align, then it means that the other participant is contributing more. So you give a higher reputation to that participant.
But is this like pairwise?
Yeah, it's done pairwise. So it's
actually NC2 reputation.
Yes. Yes. Actually, going back to your question, that actually helps in many cases, right? So in real world scenarios, we can find cases where, let's say, one client has a lot of samples about a particular class. Then a different client may have a lot of data, but may not have that particular class. So in those cases, you can actually see the reputation scores, and it actually correlates with all these distribution shifts.
Hi, thanks for the talk. I was wondering, so I liked the parallelism to the biological relationships that exist, let's say, in the food chain. Do you think that they can exist in parallel when we're training in a collaborative manner a single model? And if so, how can we model this relationship? So you talked about mutualism, commensalism, parasitism, and competition. So there might be relationships between clients. Let's say, for simplicity's sake, in the cross-silo setting, where you have like a binary competitive relationship between like two entities, and then you might have like a mutually beneficial relationship between two other entities.
Yeah, so that's why we decided to go for the decentralized approach, right? Where you can actually model these various types of collaboration, right? So within the same setting, you might have multiple parties which are different binary relationships, right? So some of the participants might have a more mutually beneficial relationship, and then some participants might be more parasitic. So how do you kind of handle these scenarios? It's easier to do it in a decentralized setting rather than a centralized approach.
But are you talking about one versus all or bilateral, like one versus one?
So just following up on the previous question, right? When you build the reputation, you actually build the reputation individually for each of the other contributors, right? So in that case, you can find out which contributors are helping you, which contributors are hurting you, and which one are not harming you in any way, but they're still there, right? So you can do this evaluation at the individual participant level or pairwise level, right? And then that helps you design better algorithms.
Great, thanks.
Okay, thank you.
Thanks, Karthik.